upload in this. Okay, good. Thank you. Anyway, now everybody see the set of slides that we were talking about last time, right? And we so far passed through the area of the understanding performance, right? And we agreed that, you know, when I look into the performance, I look into the whole entire stack from the top to the bottom, right? From algorithm that I'm trying to implement on the machine and breaking into executed operations. And this executed operation will go into the level of what programmability or programming language I will use to implement it on the machine, which is literally will affect by the compiler version and the level of optimization that has already have been embedded inside the compiler for having a smaller and optimized footprint, memory print, basically footprint. And definitely that will be indicated on the machine instructions and how many instructions per operation will be executed. And that will be transferred into the point when you are in need of the maximum frequency and the speed of the transistors. You will figure out the final execution time they are taking to execute this implementation of this algorithm. And if this algorithm need to gather information from the I/O system, like a speaker, keyboard, whatever, also the execution time, those guys, and response time, those guys will be taken, that will be taken in the full consideration when I calculate the full execution time on the system, right? To carry on in the process, you know, performance in the computer systems, you need to think about different factors while you are thinking about, and we already talked about before, right? Technology, and we say technology, how many transistors can fit on the chip. Also, that will tell you how many, what is the maximum frequency will be translated on the chip in that case. Also, the processor technology. And those two aspects we already talked about before, right? And if you guys remember, when we talked about the differences between RISC versus CISC, we came into the point that, you know, RISC is reduced in instruction set computers. All of the instruction will be running in the same time. That means that maximum frequency will be dropped down and the power consumed will be less than CISC, which is actually the vice versa, right? Also the organizational, like, you know, since, you know, we can fit a lot of transistors on the chip, we can even build multi-cores. Like, you know, the example that we ran in the top of it here, when we said that we have 6 core in the i7, right? So if I have the luxury of fitting more transistors, I can have parallelism cores that, you know, processing independent data if the algorithm naturally has some parallelism. Like, for instance, some of the astrophysics algorithms that, you know, running on the supercomputers, like, you know, Oregon National Lab supercomputers and the one in Tennessee, what is it called? Oak Ridge National Lab. Those guys have a parallel machine and they call it data flow machines. And of course, that show you high-end architecture, like, you know, ILP, MEMD, and SIMD. ILP is mean instruction level parallelism. Is there is a possibility for one instruction to be broken in parts and each part will be running in parallel? That's a type of processor architecture. Also, what is the complexity of the memory hierarchy I have? Is the memory I have at the moment is just like a big table, or it is cache passing to a main memory and this main memory passing into the hard drive, and hard drive level of it is like NVMe or SSD or whatever, ending to the USB stick that you already have it in a computer, right? Also, the quality of the I/O devices from the organizational and technology perspective. I mentioned that to you last time when I said, you know, that the jack, the connections of a high-end speakers made from gold, and even, you know, for microphones, to be sure that, you know, you are transferring the signals in a really quite fast medium. Also, in the top of that, you know, even though that you have cores, end of the day are not fully processor. But, you know, what about if your chip can have more processors that will even make it more and more stronger, right? And definitely, performance would be affected by the quality of the software. And we already mentioned about that in the programmability here, and also the operating systems and the databases you are trying to use. And moving forward to the computer systems, you will talking also about the purchasing perspective. And I also mentioned that to you, right? If you are looking into a certain performance, but you already have this amount of money, this course will allow you to understand how can you deal with this, and you can find the best fit technology that will fit the budget you already have. And also from the design perspective, what is the room for improvements you can do in the system that it will have better performance? And we're going to study something in the end of the chapter. It's called Anda's law, which is showing us where is the bottleneck in the system, so we can improving that weak part, so the whole entire system will be speeded up, and we can define how much speed up have been achieved. What are the metrics that measure performance is really looking into it. So we are looking in this chapter into the master of the matrices for the performance, which is the execution time. Do you guys agree? So if you have a computer, right? And I have my own computer, and then your friend is a common friend, and he gives both of us the same piece of program and asked us to run it, right, on our separate machine. To win this competition, your computer should finish before the other one, right? And that's called execution time. So the execution time, the definition is the time to execute one program from the beginning to the end, right? And I think you guys already have taken C, right? Hello?
Yeah, we have.
Yeah, you guys took C, right? And you learn about, if you break even your program into pieces and you call them tasks, you can say CPU time start, CPU time end, and you subtracted both of them, you will get the net time. Do you guys practice that before? Have you tried before? Yes, right. So if you go in the whole entire program and CPU start, you went in CPU end, by the end of the program, and then you subtract both of them together, you get the execution time, right? And literally, you need to know there is two different times. One is called elapsed time versus execution time. So the elapsed is basically taking the whole entire system into consideration. What does it mean? Like, I'm collecting something from a sensor connected to my computer using SPI interface. And that takes some time to move the data into a certain location in the memory. Then the memory response plus the CPU execution, that's the whole entire time is taken, is called elapsed time, because it's looking into the whole entire system time. But if you are just looking for the CPU, dedicated CPU, they call it CPU execution time. We're gonna look into this later on. Okay. Now there's another factors we can actually study, which is very important for the performance evaluation, which is called a response time. So imagine that, the time that you are asking your memory to give you a certain data from certain location, right? When the memory reply back to you, the amount of time you are waiting from the time that you send the request until you get the time is called what? A response time, right? Same thing. If you came into a certain location in the program and you would like to know exactly how much time it takes, you will start a pointer to say start time and end time, and you subtract. This is response time. So you break your program into tasks, and then you will calculate how much this task will take. So you can indirectly figure out that, execution time is a bunch of response times, right? Then there is another factors, which is metrics we're really interested into it, which is called throughput. And the throughput is what? End of the day, in a computer, we are working with a pile of data. Do you guys agree? So this data is like bytes, kbytes, megabytes, gigabyte, terabytes, whatever, right? Petabytes, whatever. So how much data per second, how much of this data per bytes per second you can process. That's called throughput. So of course, if the system take 100 gigabyte per second or bit per second, will be appreciated more than 50 gigabyte per second, right? So that's one of the factors that you are looking into it, which is a total amount of work completed in a given time. We said per second here, right? Example for that, transaction in databases. Like, if you are working in a bank and you are IT and you are looking into the packets of data moving from the transaction, drawing, depositing, whatever, how much you can finish per second, that show you whether that your system is really weak or robust. Also, the indication of how the resources are used, how many transistors are used. Of course, if the whole entire transistors on the chip will be used, that means you can get into the peak of number of transaction bytes per second, right? Very good. The throughput is very good metrics for measuring and evaluating the hardware side of the computing system, which we can call it a chip. And who is actually appreciating this metrics? The people who are working in designing processors or chip activities, basically. Makes sense? So the people in software, they like execution time. People in software like response time. People in hardware, they like to see how much their hardware can furnish per second. So that's why throughput is more into the hardware people. Okay? Component metrics. So component metrics, when I look into my whole entire performance, I shouldn't say my whole entire system doing this job and that's it. I have to break and fully study the whole entire system as a pieces. And I study looking into the reaction of every single subsystem. And of course, if I look into the macro level of the system, I will know that, there is memory and there is execution happening in the arithmetic logic unit, which belongs to the central processing unit CPU. End of the day, those are the big players. And the rest are eyes for us, right? So we have to be sure that, the memory is not making the CPU being idle or stopped because, there is some issues of moving blocks of data from here to there. You guys agree?
Yeah.
Now we are moving into the slide, which is talking about the first metrics that, which is the highest importance metrics in any benchmarking, which is the execution time and the performance. So they already define another factor, which is performance, and you considered one of the execution times. So if anybody give you execution time and asking you for the performance as a factor or rate, you say 1 over execution time. Okay? Then that will open the door for you, either that to improve the compiler, upgrade your software, or upgrade your memory, or upgrade the CPU, or upgrade the motherboard, whatever, or even the hard drive from spinning needles into SSD or NVMe or whatever, architecture is already exists as a product. How can we benefit from the execution and performance if we are trying to compare between two systems or more, right? So imagine that, I have two computers, right? I have computer A and computer B. And A has a processor and B has a processor. And I would like to compare between of them. So the ratio, which performance A over performance B, is basically what? Execution time of B over execution time of A, right? Because, it's a flip relationship. It's not straightforward. If somebody increases, automatically the other one will increase. From there, you can say execution time of A is taking longer of B or B faster than A by this ratio. Example, right? If my processor A is taking 20 seconds to finish a task, while B is taking the 25 seconds to finish the same task or program, right? Who is faster than who? So in that case, I would say execution of B over execution of A is almost 1.25. What does it mean from your point of view? That means 25% above, right? Because 1 is 100%. So A is 1.25 times faster than B. Does it make sense? I know it's simple stuff. We're gonna go in now complicated stuff, but this is very simple. Is there any questions so far?
No questions so far.
Okay. Now measuring time, measuring time. So I told you about the elapsed time, if you remember, right? So that's why I'm just reading it, because I already told about it. It's looking into the whole entire system, including IOs, operating system, idle time, whatever pieces in the system is computing or doing a process on your data until you will finish the whole executions. So that's why he look processing, IO, OS overhead, and of course the memory idle, when the memory is like stuck to give you what you requested. And of course, it's giving you an overall picture about what is the shape of your system. But if you exclude all of these, then you will end up having CPU execution time. So you are just dedicated for the processing element, which is ALU, CPU, whatever that you already have, right? So no memory effect in the CPU, no IO time is added, no effect on the multi-programming or other skills like an operating system. How can we calculate the CPU execution time? It is CPU clock cycles times the time of the clock cycles. Do you guys remember the critical path? In the critical path, you are looking into the longest path between input and output. Do you guys agree? How? There is a bunch of sequential and combinational elements in the middle, right? And I know the response time of every single element. You keep adding, accumulating them, you will come into a number, and this number will be in a second, nanosecond, or microsecond. It's a time, right? If you flip it, it will be the maximum frequency, right? So if you look into the data sheet of the processor, like i3 or i7 or i9, you will find telling you, oh, my chip is running 1.3 gigahertz, right? If you would like to know the clock cycle time, flip it. You will turn it back to time. Multiply how many cycles this task is taking, you will get the execution time. Simple, right? Make sense?
Makes sense.
So just reminding you, if you guys remember, when we had clock, the clock is two pieces, right? Is a positive, is a high and low, high level and low level, right? Then you have two edges. If I go from the low to the high, that's called positive edge of the clock. Do you guys remember that? Why, if I go from the high back to the low, it's what? The negative edge of the clock. If you are electrical and you just think about electrical, right? Those guys is RC circuit, crystal. So that means, if I charge from the low to the high, the time I take for charging the positive edge. The time I'm from the high losing the charge to be low, that's the negative edge. Make sense? If you guys studied the 3300, you will find out that in always block and Verilog, you have to go into one of the edges, and 90% of our practice on campus, I believe it was positive edge, right? Pos edge of the clock. So if you like to summarize that, so the clock period is the period of time, the whole clock taking from going high to the low, and this is periodically repeated, right? So we just care about one clock from here, which is this clock period. If somebody tell you clock frequency rate, so that means 1 over it, okay? So normally the maximum frequency in megahertz or khertz or what, gigahertz or terahertz, whatever. When you flip it 1 over it, it will be what? Second, nanosecond, picoseconds, microsecond, milliseconds, or even femtoseconds. And femto is actually 10 power minus 15. not 10 power 10, not 2 power 10 minus 10. Okay. Now, if you like to improve your performance, better for you to what? Shrink the period, right? Because if you shrink the period, what will happen? 1 over something shrinked. The denominator is small. So of course, the overall will be higher, right? So the maximum frequency will be much higher. But if the denominator is big number, 1 over big number, of course, the maximum frequency will be much lower, right? You guys agree?
Yep.
And here, basically what we're talking about, reducing number of clock cycles if you improve the performance, increasing the clock rate so the duration will get shorter. And of course, that will be a trade-off and a kind of complexity for the designer to figure out the best way without adding more resources on the chip and adding redundancy in a finite state machine, or sequential elements or combinational elements, as we had as a practice for the 2300 and 3300. Let's have an example. So CPU execution time. So if I have a computer A, it's running in a clock rate 2 gigahertz. Okay, and the CPU time, that means the CPU execution time is 10 seconds. While I'm designing computer B to have execution time 6 seconds, right? Can you please check for me how I can do faster clock, but causing that, gonna be 1.2 of time of the clock cycles? How fast must clock B would be running? That means I'm looking for the maximum frequency for my new computer B, which is a challenge for the people who work in the hardware level, right? To think about it very clear, clock rate of B is clock cycles of B divided by the CPU time, right? So gonna be 1.2 times the clock cycles, which I don't know, divided by 6 seconds. And the clock cycle of A is the CPU time of A divided by the clock rate of A, which is what? 10 seconds times the 2 gigahertz, gonna be 20 power times 10 power 9. Why? Because it's gigahertz. Do you remember? Gigahertz, basically the flip of the nanosecond. So that means 10 power 9. So now the clock rate of B is gonna be what? It's gonna be the whatever we calculated in the top here, 1.2 times 20 times 10 power 9 divided by 6. And from there we figure out that the new processor, which is lay on the computer B, has to be running in 4 gigahertz to get and fulfill the requirement of what? 6 seconds for the execution time of the computer B. Does it make any sense to everybody? Hello? Yes.
A little confused. Could you repeat that? It's kind of a little confusing to me.
Is it confusing? In what sense? Tell me.
I guess just more of I just need to actually sit down and look at it a bit more, I think.
Yeah, but feel free. If you have any question, don't hesitate, ask. But in general, I will tell you. Execution time is what? Number of cycles this program is taking in the CPU, right? Time the duration of every cycle. Do you agree?
Yes.
But we said the duration of the cycle, if you flip it, it will be the clock rate, right?
Right.
And it's gonna be in megahertz, right?
Mm-hmm.
That's basically what we did. So instead of number of cycles time the clock duration, it will be number of cycles divided by what? The clock rate. Right?
Right.
So that's why this equation came like that.
Thank you.
You're welcome. Anyway, now we have add, subtract, multiply, add, subtract, multiply, whatever. So every single operation for us, it's translated in a machine instruction as an instruction. Do you guys agree? You have to give a command, right? Execute this, do this. So I say execute add. So that's an instruction, right? So if I'm in RISC architecture, we assume that all of the instructions are taking the same number of cycles, right? So that actually show you there is a matrix is called what? CPI, which is the number of cycles per instruction. Number of cycles per instruction. In RISC, one cycle, all of them, right? What about CISC? CISC, we said it's a multiple instruction per multiple cycle per instructions, right? Which is gonna benefit from this CPI, right? Because multiplication can be done in 4 cycles. Addition maybe can be done in 1 cycle, right? So different instructions need different number of cycles. It depends on the architecture, as we said. So as I said, multiplication take more time than addition or shifting, especially if you are in CISC. Floating point, which is dealing with the real numbers, like 1.358. That's actually what real number. That means consists of fraction on the right, and you have on the left the integer, and there is the decimal point in the middle, right? So floating point is used as a representation for real numbers on computers, and that will be completely covered in chapter 3. But at least it takes much longer time than normal multiplication or addition in the integer format. So CPI here will be a very important metrics to track what's going on your system. Also, the accessibility to the memory. Maybe the memory will take 1 or 2 cycles to give you your whatever you requested, or maybe it will take 2, 3, or 4 cycles to locate what you would like to locate in the memory. So changing the cycle time, often it changes number of cycles required for various instructions. Sounds good? So if you would like to look now into the number of clock cycles we were talking about in the top, right? You remember when we said number of clock cycles, the program will take times clock duration. Now we're gonna break this into what? How many instructions I have, multiply how many cycles every instruction has. That will give you the total number of cycles, the CPU is running now, right? Make sense?
Makes sense.
Super. So if you would like to look into the equation now, the equation now have more pieces, right? It has number of instruction, time, how many cycles per instruction is taken, time, the duration of every single cycle, right? There is some programs are using categories. Like, there is a set of instruction taken 4 cycles. There is some instruction taken 6 cycles. There is some instruction taken 7 cycles. So that's actually called averaging CPI. And we're going to talk about it later. But at least we understand that, CPU time is what? Number of total cycles times the duration of cycle, or number of total cycle divided by the clock rate, or you break it to be number of instruction time the count per number cycle per instruction, CPI times the clock time, or number of instructions times the cycles per instruction divided by clock rate. So the CPI, as I mentioned, if you have a categories of instructions, like your processor have 4 categories: set of instruction running in 4 cycles, set of instruction running 12 cycles. Then we're gonna go in averaging, which is average number of clock cycles per instructions. This will be appreciated by calculating the throughput. Will be also a component metric. That means I look into the component as a CPU or pieces of the CPU, but it's not a very good for measuring the whole entire performance, especially if it's averaging. Sounds good? Also used to study the organizational way of the processor, especially if you make fixed parameters. What is the parameters that we have in the system? We have a big system, right? We have a chip, and we have a driver, we have whatever, right? So if you think that your operating system is the same, the compiler of the language you are using is the same, The same instruction set architectures. Then you can use this for looking into the processor organization. We're gonna have examples soon. Okay. Here is my example. We're gonna start with a simple one up to a difficult one. So if my computer A, the cycle time, so we don't need now the clock rate, right? The cycle time is 250 picoseconds. And the CPI is 2.0. Somebody will tell me, why, Dr. Ali, we have 0.0? Because we have fraction can be represented in the CPI. So that, because there is averaging in the previous slide, right? So that's why CPI is 2.0, not just 2. Computer B is running in the cycle duration 500 picoseconds, and the CPI is 1.2. If we consider it's the same instructions architecture and same number of counts, of instruction per instructions, which one is faster and how much they are really fast? Very easy practice, right? If we go into the equation we have in the top, number of instructions is I, time the number of cycles per instruction, 2, times the cycle time, 250. Total, it's gonna be number of instruction, I call it I, time 500 picoseconds. Then in B, same thing I will do, 600 picoseconds. Then if you remember the ratio thing, right? So I'm gonna say CPU time of B divided by CPU time of A. So gonna came into what? 1.2, because both of them I will be neglected. So I can come into a conclusion, A, performance of A, of course, better. So A is faster than B by this ratio, which is 1.2. Does it make sense? Is it clear to everybody?
Makes sense.
Okay. Now, the equation for averaging CPI. If I would like to average a CPI, how I'm going to average it, right? So CPI is a different classes of an instruction. I told you there is some set of an instruction running with 4 cycles, some set is running 5 cycles, and so on. So the equation is really easy, averaging, right? So it's summation. How many groups of instruction I have is running from I equal 1 to n, and what is the weight, what is number of cycles per this group, time the instructions family, okay, which is the number of instructions of I, number of instruction we have in this class. And there is another one, is called weighted average CPI, which is basically relativity here. So, you know, you have a CPU clock cycles divided by number of instructions. But now I'm going to break it into CPI time the C, which is the category of the instruction, divided by number of instructions. Equation theoretically by itself is confusing. Better to look into example and applying it, then you know it will stick in our head. So that's why we have example here. So we have an alternative compiled code sequences using instructions. And we have 3 different categories or classes C in the 2 computer sequences. One is 1 and one is 2. Okay. A, B, C. A, CPI of classes is 1. B is 2. C is 3. While in the instructions compiler, sequence 1, A is taken 2 times, B is taken 1, C is taken 2. And the difference in the sequence 2. Now, what we need to do, we need to calculate the average CPI from the equation we have in the top. How can we do this? So look into the row of the IC sequence 1. If you calculate here, A and B and C, end of the day is inside it, right? So A is taken, what is the weight? 2, right? B is taken, what is the weight? 1. C is taken the weight 2. So 2 plus 1 plus 2, what is the total will be? 5. Right? We're gonna do the same thing with what? Sequence 2, 4 plus 1 plus 1. Here is 6. So far, so good. Now, what we're gonna do, we're gonna take it one by one. So A is 1 times 2. So gonna be what? 2 times 1, because sequence 2 times 1 plus 1 times 2 plus 2 times 3 summation, because we made the summation in the top here. So the total will be what? 10. What is my average? 10 over 5, 2.0. So now I calculated the official CPI of the system of sequence 1 is averaging here. While in sequence 2, we're going to do the same practice, right? So it's a 4 times 1, 1 times 2, 1 times 3. Sum them together, it is 9. So the CPI here in this case is going to be 9 over the total 6. It's going to be 1.5. Does it make sense to everybody?
Yes.
Feel free to stop me in the middle if there's something is not clear. I know it's easy now, but later on when the course will get into deep details, we might have some complicated stuff. Sounds good? Now, with the knowledge of this equation, we can draw a very nice performance summary, right? Which is, what is the CPU time? It is the number of instruction in the program, right? Times how many cycles per instructions, right? Time, how much time it takes for the cycle, right? You guys agree? Now, we look into the performance study. So if you remember in the beginning of the lecture today, we talked about the algorithm, the programmability in the language, we talked about the compiler, and we talked about also the number of instruction per chip. Let's see how CPI will be working on it, right? So algorithm, right? Number of instructions will be affecting the total performance. So possibly, based on understanding we have today, CPI is a good player that will affect on the algorithm performance. Programmability, right? So the compiler will end up decreasing or increasing number of instructions, which is translating CPI in the middle. So that's also CPI a good player to help me to understand whether that's programmability or the compiler version is really good enough or it needs to be excluded or upgraded, which is replying to you in the third line, right? Compiler affect number of instructions CPI. Also, instruction set architecture from the technological part of the chip is affected by number of instructions because, you know, the hardware designer is making the varieties for you, and the CPI time, and also the duration of the clock, which is basically the maximum frequency you can achieve as a chip, which is the clock rate, 1 over the clock rate. Sounds good? Now, if I look into the two architecture I was talking about last time, RISC versus CISC, right? So if you look to RISC, if you increase instruction per program, but you decrease, you're gonna decrease the CPI and the clock cycle time because the instruction end of the day, all of them taking the same duration of cycles. You guys agree? While in CISC, decreasing the instruction per program will be consequence increasing the CPI and the clock cycles because, of course, every single instruction, it might has its own class because it can have different number of cycles, which is actually indicating the whole entire process will be more complex than RISC. So far, what we have done today, we studied a very straightforward equations for performance metrics from the execution time perspective, from the response time perspective, from the throughput perspective. Then we move into breaking the execution time and learning that there is elapsed time which is looking for the overall time of the system versus the time of the CPU, excluding the IO and idle from the memory and other peripherals. And we look into who is actually tying this to technology by the duration of the cycle, and that will be breaking into the CPI, which is number of cycles per instructions. And if there is a classes of the instructions, which is reflecting something is called average CPI, and we look into the CPU time, which is an instruction program times the clock cycle per instruction, second per cycles, and how it's affecting the performance into the 3 or 4 lines we mentioned. And we took the RISC and CISC as an architecture example and applying those performance into it, so we can figure out if some increases in the instruction program happen, what will happen in the CPI and clock cycle, whether it will be increased and decreased based on the simplification or complication the architecture has. So far, so good?
Yeah.
Good. We can stop here in the uniprocessor performance, and we can resume that next time. Any question? You already have a copy of these slides, right?
Yes.
Super. So we're gonna continue next time for this. And also, you guys, I will send you the list of the GitHub groups, perhaps tomorrow or tonight, and the possible project for every single group. So you guys think about it until coming Wednesday. If you like, maybe 10 minutes or 20, 15 minutes in the beginning of Monday, we can actually go through all of the projects so you guys will fully understand what I want. Sounds good?
Yeah.
Any question? Yes. Any question? Any question? Yes, go ahead.
Professor,
Yes.
are there any things we can start practicing for like any future tests or anything?
Okay, so basically, once we finish the chapter 1, I will be giving you a set of questions coming from the book, okay? And you will take like a 1 week to study them and give me the answers, like a homework. There is no grade weight on the homework, because after that, I will give you the answers. But the whole idea that, once we finish the chapter, my philosophy, finish chapter, give you homework, you practice the homework, I give you the answers like in a formal way, then you study it very well, then you go in a quiz, then you apply this, then you will move forward to the next topic, do the same thing, and so on. Then the midterm will be coming to cover everything, and we move forward.
Thank you, Professor.
Make sense?
Yes.
So normally, my midterms doesn't like go, the quizzes doesn't go into like accumulative, but the midterms accumulative. Okay? Any other questions or concern? What I want you guys to do, I want you, if you have the time, rewatch the video again, because I will post it on the modules of the course under Canvas week number 2 for this lecture and other lecture as well. And also look into the slides. So if you remember, if you look very carefully, today we give like a very simple equations, right? Some of the problems, with the midterm quiz number 1, people will make mistake like A faster than B, they would say B faster than A, you know what I mean? So that's why I want you to understand the concept. Okay?
Got it.
Also, before we end with chapter, I will give a lecture with bunch of like complicated equations and questions, and we can go in the problems and I solve it with you, and then you can ask. So then, you will be full prepared for the quiz. Okay, Duke?
Thank you.
Yeah.
Thank you.
Professor.
So it was my pleasure to talk to you guys today, and God bless you. And I'm looking forward to meet you. Are we gonna meet on Monday? Monday would be what? Let me check. Are you guys gonna be on campus on Monday or what?
One more week of online.
No, the following week. Yeah.
We'll be on campus during the
Yeah.
14th.
So maybe we still have some time. Yeah, yes, that's true. But anyway, looking forward to see you guys soon. Okay,
Thank you, Professor.
that's good. God bless you.
Well, Professor.
Bye bye.
Thank you,
Thank you, Professor.
Bye bye.